So the last thing I want to discuss is how kinetic energy, which involves speed and mass and temperature and all these things, contributes to rates of diffusion and effusion, which are two different things. So to start off there, we have to have a working definition of what kinetic energy is. And really, before we can get there, we have to understand what these two graphs are showing. Now, these are called Maxwell-Boltzmann distributions because they're named after two different people who kind of came up with the same thing. And when you see the term distribution, all that is a statistical definition. And it just means that it is more than one value. And what you'll see here is that each of these graphs is showing that there is more than one speed, that there is a range of speeds that are being shown. So that's important to see. So these are showing two different things. So this top graph is showing how temperature affects speed, and the bottom graph is showing how the different gas type, which is another way of saying mass, affects speed. And you will see that both of them have an effect. So temperature and mass affect speed. That should be common sense to you. So if you stop and think, how should temperature affect speed? Well, what you can see here is that the higher temp gives you faster speeds. Higher temp equals faster speeds. Again, common sense. If you take honey out of the cabinet and it's like really slow and viscous, if you need to be able to pour it out of the container, you zap it in the microwave for like 20 seconds. You heat it up and then all of a sudden the honey flows faster. So that is a direct correlation there. Temperature gives you faster speeds. Now in terms of mass, if we look at these, the heavier things, right? So this is xenon, and this one over here is helium. So looking at the extremes, what do we see here? Is the heavier thing faster or slower? Well, here it's slower. So heavy equals slower speed. So while the first instance is showing me something that is direct, right? More temp, more speed. In terms of mass, we have something that is inverse, right? More mass, slower speed. Okay, now I want you to look at the shapes of these graphs, and I want you to notice that as you increase the temperature or you increase the mass, what is happening to the shape? Well, it is both shifting to the right and it is squishing down. So it's doing both of those things, all right? And that's what ends up happening in these Maxwell-Boltzmann distributions. And I'm going to show you some free response questions where they actually have you draw on top of a given graph what it would look like at a higher temperature. And the thing you need to know is that it both squishes down and shifts to the right. Okay, so these two graphs are not quite Maxwell-Boltzmann distributions. They are variations of that because these are showing kinetic energy. And it's the same thing, difference in temperature and difference in mass. So what do we see here? Temperature has an effect on kinetic energy. Higher temp equals higher kinetic energy. But what about the mass? Well, all of those gases have the exact same kinetic energy. So mass doesn't seem to matter. Well, that's interesting, but I want you to notice that mass doesn't seem to matter as long as they are at the same temperature. Okay? Because the same temperature is going to give you the same kinetic energy regardless of the substance. That is what is important. So all of this is to say you don't need to know this formula, but this is the formula for kinetic energy. 1/2 mv squared, with m being mass and v being velocity, which is just the physics word for speed. So mass should matter. It's in the equation. So why doesn't my higher mass give me higher kinetic energy? Well, because higher mass equals slower speed, right? That's what we saw in the Maxwell-Boltzmann distribution on the other side. So when you increase the mass, you slow down the speed so that these two things essentially stay the same. So the thing to remember here is, since kinetic energy is essentially measured by temp, right? That's how we represent it. So things at the same temp have the same kinetic energy. That, I can guarantee you, is going to be a multiple choice question somewhere on the exam. Otherwise, if you think about it, increasing the temperature is going to increase the speed, and it would increase the kinetic energy. So this graph on the left, this is common sense. It's the graph on the right that tends to trip people up, because you would think that the mass would matter. So you need to remember that as long as you are looking at the same temperature, you are not going to have a change in kinetic energy regardless of the mass of the individual particles. So what does all of that mean for these two words, diffusion and effusion? Well, before I look at all the rest of those words, let's talk about what these two things are. So diffusion is something that you mention in biology, but you're talking about particles in a liquid. And here what we mean is the mixing of one gas into another. And the classic example is spraying perfume in a corner of a room. And you know that over time, that perfume is going to spread out throughout the room, so that eventually, if you were standing in the opposite corner of where it's being sprayed, you will end up smelling it because it diffuses or spreads out throughout the room. Okay, effusion. Well, effusion is when gas particles move through a tiny hole. Okay, so that would be like if you have say you've got a divider here, that divider has got a hole, and then I have little particles over here. See all these gas particles, and then one of them moves through that tiny hole to come over here. So how fast that process can happen is similar to how fast a gas can diffuse throughout an entire space. Okay, so it's really easy when you look at the diffusion or the effusion diagram here, a little particle trying to go through a little hole. Well, what might affect that? And the obvious thing is, well, the size of the particle that has to fit through the tiny hole. And sure enough, what we see is that the rate of diffusion or effusion is going to be based on the molar masses. And in general, we say it's based on the square root of the ratio. Okay, you no longer have to calculate this. What you need to do is reason through and say that gases with tiny masses have faster speeds, right? Because that's what the Maxwell-Boltzmann distribution showed. Tiny masses have faster speeds and will diffuse, effuse faster. How much faster? Well, it's a combination of the square root of the ratio of their masses. But that's really it. You're not typically going to have to calculate that, but I'm going to go ahead and go through the calculation that's done in your problem set so you can kind of see that. Okay, so this is a standard type of old question that used to be asked. Carbon monoxide effuses, effuses at a rate that is 2.165 times faster than that of an unknown noble gas. Calculate the molar mass of the unknown gas and identify it. So we have carbon monoxide and we have an unknown noble gas. Those are our two things. And it says that carbon monoxide is faster. So that should immediately tell you, is carbon monoxide bigger or smaller than the noble gas? Well, if carbon monoxide is faster, faster means smaller mass. That's what it means by definition, that this is a smaller mass. Okay, well, what is the mass of carbon dioxide? Well, it's one carbon and it's one oxygen, that's mono, so that's 12 plus 16, so that's 28, 28 and change, but 28 grams per mole. That's that molar mass. Okay, so if that's that molar mass, then I know that that is 2.165 times faster than the other one. So the formula that you'll see is that the ratio of the rates is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. And in your reading guide, I said always make smaller gas equal to number 1 and heavier gas equal to number 2. So they give me the ratio of rates. It's 2.165. And then what I don't know is this molar mass of gas 2. But what I do know is the molar mass of gas 1, which is 28. So it's the square root of 28. Okay, so if I need the molar mass of gas 2, this is in a denominator, it's divided, so to clear it out I need to multiply, so that's 2.165 times the square root of 28. You need to know how to enter that in your calculator and not mess it up. So if you do all that in your calculator, go ahead and try it out. What you should get is 11.456 blah 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 blah. That equals the square root of the molar mass. So how do I just get the molar mass? Well, you simply square this value. You square both sides. And if I square both sides, I'm going to get approximately 131. So my molar mass is 131. So how do I know what gas that is? Well, they tell me it's a noble gas, and noble gas are in group 18. So simply scan down the periodic table on the far right-hand side in group 18, look at all their molar masses, or their atomic masses, and see who matches up to 131. And what you would find, xenon. So the unknown gas is xenon.